In module 1, we have learned about the series solution of the hypergeometric equation, which is the hypergeometric function. We have also seen the differentiation of the hypergeometric function, the integral representation of the hypergeometric function. In this module, in module 2, we will learn about the confluent hypergeometric function. With a simple substitution, we can change the usual hypergeometric equation into an equation whose solution is going to be the confluent hypergeometric function. In this module, we will learn about the confluent hypergeometric function. Please recall the usual hypergeometric equation, which is given by equation number 1, that is x into 1 minus x d2y dx square plus gamma minus alpha plus beta plus 1 into x dy dx minus alpha into beta into y equal to 0. Now, in this differential equation, we replace x by beta, and if you do that, you will be getting equation number 2. So, all you have to do is in equation 1, you replace this x by beta, this x by beta, and so on. So, in equation number 2, which you obtain after replacing x by beta, it is simplified and we get x into 1 minus x by beta d2y dx square plus gamma minus 1 plus alpha plus 1 by beta into x into dy dx minus alpha into y equal to 0. And we denote this function by f of alpha, beta, gamma and x by beta. Now, as beta tends to infinity, equation 2 reduces to x y double dash plus gamma minus x into y dash minus gamma y equal to 0. So, what you have to do is in equation number 2, we make beta tends to infinity, and we know if beta tends to infinity, 1 by beta tends to 0, and hence this particular term x by beta vanishes. This particular term alpha plus 1 divided by beta vanishes, and we are left with the simplified equation of the form x d2y dx square plus gamma minus x into dy dx minus alpha into y equal to 0, and this is called the confluent hypergeometric differential equation or Kummer's equation. Before moving further, let me explain the Pochhammer's symbol. The Pochhammer's symbol is defined as, the notation is alpha suffix n, which is equal to alpha into alpha plus 1, alpha plus 2 dot 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 alpha plus n minus 1, with alpha 0 is equal to 1 and n is a positive integer. Please note, the easy way to remember this is, if it is alpha suffix n, the ending term will be n minus 1, which is 1 less than this particular integer. So, this symbol alpha n, which is equal to alpha into alpha plus 1 into alpha plus 2 plus dot 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 alpha plus n minus 1, we multiply both numerator and denominator by 1.3.2 dot 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 alpha minus 1 divided by 1.2.3 dot dot alpha minus 1. And if you do that, the numerator becomes 1.2.3 dot dot alpha minus 1 into alpha plus 1 into alpha plus 2 dot 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 alpha plus n minus 1, which is nothing but alpha plus n minus 1 factorial. And in the similar argument, we can say 1.2.3 dot dot alpha minus 1 is alpha minus 1 factorial. And since gamma n is equal to n minus 1 factorial, we can write alpha plus n minus 1 factorial is equal to gamma function alpha plus n, and alpha minus 1 factorial is equal to gamma function alpha. So, this is just a simplified form of the Pochhammer's symbol alpha suffix n, and which we will be using in many problems and theories. So, the solution of the confluent hypergeometric differential equation may be written as limit beta tends to infinity f of alpha comma beta comma gamma x by beta is equal to, we substitute the definition of f here, and we will be getting limit beta tends to infinity summation r equal to 0 to infinity alpha suffix r beta suffix r divided by gamma suffix r into r factorial x by beta whole to the power r, which can be simplified as limit n beta tends to infinity summation r equal to 0 to infinity alpha suffix r beta suffix r divided by r factorial gamma suffix r beta to the power r x to the power r. Now, please note the expression beta suffix r and beta to the power r as beta tends to infinity. If we simplify this, we will be getting limit beta tends to infinity beta suffix r divided by beta to the power r, and this by Pochhammer's symbol, if you expand this, you will be getting beta into beta plus 1 into beta plus 2 dot 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 beta plus r minus 1, and if beta r, this can be written as beta into beta dot 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 r times. If I now divide each term by each of these betas, I will be getting 1 plus 1 by beta, 1 plus 2 by beta dot 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 1 plus r minus 1 by beta. And as beta tends to infinity, 1 by beta tends to 0, and we will be getting 1 by beta tends to 0, 2 by beta tends to 0 dot 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 r minus 1 by beta tends to 0, and hence this whole expression is equal to 1. This result we use in this expression. So, as beta tends to infinity, beta suffix r divided by beta to the power r, they tends to 1, and we are left with a simplified version of the expression as summation r equal to 0 to infinity alpha suffix r divided by r factorial gamma suffix r x to the power r, which we denote by f of alpha gamma x. So, the function f of alpha gamma x is called the confluent geometric function. We now look into the solution of the hypergeometric differential equation when x is equal to 0 and gamma is not an integer. We assume the solution of the form y equal to summation r equal to 0 to infinity a 0 x to the power k plus r, where a 0 not equal to 0. We differentiate this expression twice to get dy dx, which is y dash, is equal to summation r equal to 0 to infinity a r k plus r x to the power k plus r minus 1, and y double dash is equal to summation r equal to 0 to infinity a r k plus r minus 1 x to the power k plus r minus 2. We substitute these values of y, y dash and y double dash in the equation x y double dash plus gamma minus x into y dash minus alpha y equal to 0, and we will get equation number 3, which is summation r equal to 0 to infinity a r k plus r into k plus r minus 1 plus gamma times k plus r x to the power k plus r minus 1 minus summation r equal to 0 to infinity a r k plus r plus alpha into x to the power k plus r equal to 0. Therefore, the required indicial equation is, which we obtain by equating the lowest power of x to 0, and in this case the lowest power is obtained from the coefficient of x to the power k minus 1, and our required indicial equation is a0 multiplied by k into k minus 1 plus gamma k equal to 0. And since a0 is not equal to 0, the required values of k are 0 and 1 minus gamma. To obtain the recurrence relation, we now equate to 0 the coefficient of x to the power k plus n, and we get k plus n plus 1 into k plus n plus gamma into a n plus 1 minus k plus n plus alpha a n is equal to 0. Rearranging the terms, we will get a n plus 1 is equal to k plus n plus alpha divided by k plus n plus 1 k plus n plus gamma a n. The first case, we put k equal to 0, and using the equation 4 we will get the recurrence relation as a n plus 1 is equal to n plus alpha divided by n plus 1 into n plus gamma a n, given by equation 5. Putting n equal to 0, 1, 2, 3 dot 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 in equation 5, we get a1 is equal to alpha by gamma into a0, a2 is equal to 1 plus alpha divided by 2 times 1 plus gamma into a1, where we substitute the value of a1 from the previous expression here, and we get a2 is equal to alpha into alpha plus 1 divided by 1 dot 2 into gamma into 1 plus gamma into a0. In the similar manner, we can calculate a3 is equal to alpha into alpha plus 1 into alpha plus 2 divided by 1 dot 2 dot 3 into gamma plus 1 into gamma plus 2 a0. We next substitute the values of a1, a2, a3 in the series y equal to summation r equal to 0 to infinity a0 x to the power k plus r, and we get y equal to a0 multiplied by 1 plus alpha by gamma into x plus alpha into alpha plus 1 divided by 1 dot 2 into gamma plus 1 x square plus alpha into alpha plus 1 into alpha plus 2 divided by 1 dot 2 dot 3 into gamma into 1 plus gamma into 2 plus gamma x cube plus dot dot dot. We next substitute a0 equal to 1, and we get our confluent hypergeometric function of first kind as f alpha gamma x, which is defined as 1 plus alpha by gamma into x plus alpha into alpha plus 1 divided by 1 dot 2 to gamma into gamma plus 1 x square plus alpha into alpha plus 1 into alpha plus 2 divided by 1 dot 2 dot 3 gamma into 1 plus gamma into 2 plus gamma x cube plus dot dot dot. Next, we put k equal to 1 minus gamma, and using the equation 4 we get a n plus 1 is equal to alpha minus gamma plus 1 plus n divided by 2 minus gamma plus n into n plus 1 a n, which can be written as a n plus 1 is equal to alpha dash plus 1 divided by gamma dash plus n into n plus 1 a n, where alpha dash is equal to alpha minus gamma plus 1, gamma dash is equal to 2 minus gamma. We next put n equal to 0, 1, 2, 3 in equation 6, and we obtain a1 equal to alpha dash by gamma dash a0, a2 is equal to 1 plus alpha dash divided by 2 into 1 plus gamma dash into a1, where we substitute the value of a1 from the previous expression, and we get a2 is equal to alpha dash into alpha dash plus 1 divided by 1 dot 2 gamma dash into 1 plus gamma dash A0. In the similar manner, we can calculate A3 is equal to alpha dash into alpha dash plus 1 into alpha dash plus 2 divided by 1 dot 2 dot 3 into gamma dash into 1 plus gamma dash into 2 plus gamma dash A0. Substituting the values of A1, A2, A3 in the series y equal to summation r equal to 0 to infinity A0 x to the power k plus r, we will get y equal to A0 x to the power 1 minus gamma into 1 plus alpha dash by gamma dash into x plus alpha dash into alpha dash plus 1 divided by 1 dot 2 gamma dash into gamma dash plus 1 x square plus alpha dash into alpha dash plus 1 into alpha dash plus 2 divided by 1 dot 2 dot 3 gamma dash 1 plus gamma dash 2 plus gamma dash into x cube plus dot dot dot. Therefore, we get our confluent hypergeometric function of second kind as y equal to x to the power 1 minus gamma f alpha dash gamma dash x. We now substitute the value of alpha dash and gamma dash, and also we put A0 equal to 1, and we get the confluent hypergeometric function of second kind as y equal to x to the power 1 minus gamma f of alpha minus gamma plus 1 2 minus gamma x. And hence, we conclude the general solution of the confluent hypergeometric differential equation is given by y equal to a times f alpha gamma x plus b times x to the power 1 minus gamma f of alpha minus gamma plus 1 2 minus gamma x, where gamma is positive and capital A and capital B are arbitrary constants. We have just learned about the solution of confluent hypergeometric equation. By a simple substitution, we have seen that we can convert our usual hypergeometric equation into a confluent hypergeometric equation, and we have obtained the confluent hypergeometric series of first kind and second kind as two linearly independent solutions of the confluent hypergeometric equation. Next, we will look into the differentiation, the integral representation of the confluent hypergeometric function. We now look into the differentiation of confluent hypergeometric function. So, here we have to show that if f alpha beta x be the confluent hypergeometric function, then ddx of f alpha beta x is equal to alpha by beta f of alpha plus 1 beta plus 1 x. We use the definition of the confluent hypergeometric function, and we get f of alpha beta x is equal to summation r equal to 0 to infinity alpha suffix r divided by beta suffix r into r factorial into x to the power r, where alpha suffix r is equal to Pochhammer's symbol, which we have defined earlier. We next differentiate both sides of the above expression with respect to x, and we get ddx of f of alpha beta x is equal to summation r equal to 0 to infinity alpha suffix r divided by beta suffix r factorial into r into x to the power r minus 1, which is equal to summation r equal to 1 to infinity alpha suffix r divided by beta suffix r into r minus 1 factorial x to the power r minus 1. Please note here r factorial and r, they cancels to give you r minus 1 factorial, and hence here from r equal to 0 to infinity we have replaced it by r equal to 1 to infinity, because for r equal to 0 r minus 1 factorial is undefined. We next substitute r by m plus 1, and we get ddx of f alpha beta x is equal to summation m equal to 0 to infinity alpha m plus 1 divided by beta m plus 1 m factorial x to the power m, which can be simplified as summation r equal to 0 to infinity alpha into alpha plus 1 suffix m divided by beta into beta plus 1 suffix m factorial x to the power m. Hence, we now take this alpha and beta out of the summation sign and we will get equation number 9, which is ddx of f of alpha beta x is equal to alpha by beta summation m equal to 0 to infinity alpha plus 1 suffix m divided by beta plus 1 suffix m into m factorial x to the power m. Therefore, we get our required result, which is ddx of f of alpha beta x is equal to alpha by beta f of alpha plus 1, beta plus 1 and x, given by equation 10. Next, we look into the integral representation for confluent hypergeometric function. Here we have to show that if f alpha beta x be the confluent hypergeometric function, then f of alpha beta x is equal to gamma function beta divided by gamma function alpha into gamma function beta minus alpha integration 0 to 1 minus t whole to the power beta minus alpha minus 1 t to the power alpha minus 1 e to the power xt dt. This expression can be again written in the form f of alpha beta x is equal to 1 by beta function alpha into beta minus alpha integration 0 to 1 minus t whole to the power beta minus alpha minus 1 t to the power alpha minus 1 e to the power xt dt, where beta is greater than alpha greater than 0. So, basically we have to prove any one of the expression and the other will come automatically. So, we start with the definition of the confluent hypergeometric function, which is f alpha beta x is equal to summation n equal to 0 to infinity alpha suffix n divided by beta suffix n into x to the power n by n factorial, which is represented by Pochhammer's symbol. And this can be simplified as summation n equal to 0 to infinity gamma function alpha plus m divided by gamma function alpha into gamma function beta divided by gamma function beta plus n into x to the power n divided by n factorial. Please recall the Pochhammer symbol where we have expressed alpha suffix n in terms of the gamma function. So, here basically we are using that as a formula. The previous expression can be simplified in the form gamma function beta divided by gamma function alpha into gamma function beta minus alpha summation n equal to 0 to infinity gamma function beta minus alpha gamma function alpha plus n divided by gamma function beta minus alpha plus n into x to the power n by n factorial. Using the definition integration 0 to 1 minus t whole to the power p minus 1 t to the power q minus 1 dt is equal to beta function pq, which is equal to gamma function p gamma function q divided by gamma function p plus q, where both p and q are positive. We will get gamma function beta divided by gamma function alpha gamma function beta minus alpha integration 0 to 1 minus t whole to the power beta minus alpha minus 1 t to the power alpha minus 1 summation n equal to 0 to infinity x t whole to the power n divided by n factorial dt. And this can be written in the simplified form as gamma function beta divided by gamma function alpha gamma function beta minus alpha integration 0 to 1 minus t beta to the power minus alpha minus 1 t to the power alpha minus 1 e to the power x t dt, which can be written as 1 by beta function alpha beta minus 1 alpha integration 0 to 1 minus t whole to the power beta minus alpha minus 1 t to the power alpha minus 1 e to the power x t dt. Therefore, equation 11 and equation 12 gives the integral representation for confluent hypergeometric function, and both we can take our required results. Next, we look into the Kummer's relation, which says that if f alpha beta x be the confluent hypergeometric function, then we have to show f of alpha beta x is equal to e to the power x f of beta minus alpha beta minus x. Now, from the integral representation of confluent hypergeometric function, we will get f alpha beta x is equal to gamma function beta divided by gamma function alpha gamma function beta minus alpha integration 0 to 1 minus t whole to the power beta minus alpha minus 1 t to the power alpha minus 1 e to the power x t dt, given by equation number 13. We replace alpha by beta minus alpha and x by minus x in equation 13, and we will get f of beta minus alpha beta minus x is equal to gamma function beta divided by gamma function beta minus alpha gamma function beta minus alpha integration 0 to 1 minus t whole to the power beta minus alpha minus 1 t to the power beta minus alpha minus 1 e to the power minus x t dt, which can be simplified in the form gamma function beta divided by gamma function beta minus alpha gamma function alpha integration 0 to 1 minus t whole to the power alpha minus 1 beta to the power beta minus alpha minus 1 e to the power minus x t dt. We substitute 1 minus t equal to u, and we get the required expression as gamma function beta divided by gamma function beta minus alpha gamma alpha integration 1 to 0 u to the power alpha minus 1 minus u whole to the power beta minus alpha minus 1 e to the power minus x 1 minus u minus du. We use this negative sign and interchange the limits, and in the next step we will get gamma function beta e to the power minus x divided by gamma function beta minus alpha gamma function alpha integration 0 to 1 minus u whole to the power beta minus alpha minus 1 u to the power alpha minus 1 e to the power x u du. We simplify and get e to the power minus x gamma function beta divided by function alpha gamma function beta minus alpha integration 0 to 1 minus t whole to the power beta minus alpha minus 1 t to the power alpha minus 1 e to the power x t dt, and which is equal to e to the power minus x f of alpha beta x. And hence we conclude f of beta minus alpha beta minus x is equal to e to the power minus x f of alpha beta x, which implies f of alpha beta x is equal to e to the power x f of beta minus alpha beta minus x, which is our required result. Summing up, in this module we have learned about the confluent hypergeometric equation and confluent hypergeometric series of first kind and second kind. We have also looked into the differentiation and the integral representation of the confluent hypergeometric series. In our next module 3, we will look into some excellent examples of hypergeometric series and confluent hypergeometric series. Thank you.